Hello everyone. Well, we have one more object for which we need to be able to calculate its rotational inertia. This is one of the ones required by the AP curriculum for which you might need to actually do this derivation on a test. So, this is the same thin rod we used in a previous one of mass m and length L, but this time the axis is perpendicular to the rod and through one end. You might remember that we figured out or we calculated the rotational inertia of a rod of mass m and length L with an axis through the center of mass and found it to be about 1/12 ml squared when we did the calculus. Right? Well, this time the axis is going to be through one edge. Right? So now it's all the way out here. So what is that going to do to the rotational inertia? Well, I'm going to do this problem two ways because we can. One way, I'm going to do the calculus, and I'm going to show you how to use different limits of integration in this case than we did in the previous iteration of this. And then I'm going to show you how much easier it is to use the parallel axis theorem to figure this out. Okay, so first, the long way, the calculus. I'm going to do this fairly quickly because it's very similar to what we did earlier. So, the rotational inertia is going to be equal to the integral of r squared dm. Right, which means we got to sum up all the little mass increments. We're going to change r to x because it's one-dimensional. Right, we consider a thin rod to be one-dimensional, have no width or thickness to it. Here's our little mass increment. Our little mass increment has a mass we will call dm and a thickness we will call dx. Right, so these are the dx and dm of the little mass increment. Right? And to do the integral, we've got to sum up all of these little pieces. But here's the problem. Each little piece is a different distance x away from the axis of rotation. The mass is not what we're changing. So we can't integrate x with respect to m, right? Because those are two different variables. So we need to do a change of variable. How do we do that? Well, like we did before, because this is a one-dimensional thin rod, we are going to use the linear density, which is uniform for this thin rod. So the linear density, lambda, is the total mass over the total length. But the linear density can also be written as dm over dx. Right? Notice this is linear density, mass per unit length, mass per thickness, right? As opposed to the regular density, which is mass per unit volume. So that means if we solve here, dm is lambda dx. If we plug that in, we will change the variable. And now that we are going to be integrating with respect to x, we can choose our limits of integration. Right, so if we pick up a little mass increment all the way over here on the left, that will have a position of 0 from the axis of rotation. Right? And if we sum them up all the way to the other end of the rod, one on the far end of the rod would be a distance L away from the axis of rotation. Hence, we are going to do the integral from 0 to L of x squared lambda dx. Right? Plug in the lambda dx for dm here. So everybody see why our limits of integration this time are 0 to L. If you remember, when the axis was the center of mass, our limits of integration were negative L over 2 to capture this end, and positive L over 2 to capture that end, and everything in between. Okay. So lambda is a constant, so it can be pulled outside the integral. So we have lambda times the integral from 0 to L of x squared with respect to x. The integral of x squared is simply 1/3 x cubed, add 1 to the exponent, divide by the new exponent, which we will evaluate at the upper limit, minus evaluating it at the lower limit. But of course, when you plug a 0 in there, you just get 0. So this leaves us with a rotational inertia of lambda L cubed over 3. But I don't want the rotational inertia in terms of lambda. I want it in terms of m and L in the original statement. But remember that since it is a uniform density, the linear density of the entire rod is the total mass over the total length. So we plug that in for lambda. One of the L's on the bottom, or the L on the bottom, cancels one of the L's on top, and we get 1/3 ml squared. This is for a thin rod about an axis through one end. Okay, through one end. If you compare it, right, the center of mass one was 1/12 ml squared. This one's 1/3 ml squared on the end. 1/3 ml squared is bigger than 1/12. Why is there more rotational inertia here? Well, it's because the masses can be further away. Like I said, through the center of mass, the furthest away a piece of mass could be is L over 2. But with the axis on one end, now the mass can be as much as L away from that. And remember that the distance that the mass is predominates because it's the r squared, right, part of the equation. Okay, so that's why we could have predicted here, and probably should have, that we would get a answer that's bigger than the one through the center of mass. Now, that was the long way, and you could do that, right? But imagine doing that for any point, any random point they put in here, right? You would have to be very careful. Really, this is where it would change, would be right here, right? You'd have to be very careful with the limits of integration if you were picking different points to have the axis through. But if we do the parallel axis theorem version, much easier. We know the rotational inertia about the center of mass. That's 1/12 ml squared. Here's the center of mass. Right? H is the distance from the center of mass to the axis of rotation, which would be what? L over 2, if this is the center of mass. The mass of the rod is m, so we don't have to change anything there. So we get this. The rotational inertia about the center of mass is 1/12 ml squared plus m h squared. H is L over 2 quantity squared. Square that. That's 1/4 ml squared. What's 1/12 ml squared plus 1/4 ml squared? 1/3 ml squared. 4 steps. Writing everything out. Right? And you find the rotational inertia about that end. And imagine finding it at some point out here. As long as you know how far away that point is from the center of mass, which is the center of the rod, you could do this same process over again very quickly. Much quicker than doing the entire calculus proof, right, over. This is the power of the parallel axis theorem. Once you know the rotational inertia about the center of mass, it becomes relatively easy to figure out the rotational inertia about any other axis. So these are all the ones that you need to know now, and you need to be able to also do the proofs.